Okay, Assalamualaikum and good day again, right? So here we are, okay, with the example for the shear resistance, okay, at ULS, right? So what we are going to do here, okay, we are going to design, okay, the shear reinforcement for our section, right? So we have one example here, okay, whereas the beam cross section, okay, shown in the figure is constant over a 30-meter simply supported span, okay, with a parabolic tendon profile and an eccentricity varying between 300 mm, okay, at the ends and 750 mm at mid-span, right? Okay, so we can see here, okay, that we have the eccentricity, right? So which is at the ends also, okay, we have eccentricity, okay, as well as at the midspan, right? So this eccentricity, okay, are measured below the neutral axis in both cases, okay, and the beam supports an ultimate uniformly distributed load of 40 kilonewton meter and FCK of 35 Newton per millimeter square, right? So the given design data are the pre-stress force after losses, okay, which is 2,590, right? Okay, so in this value, okay, the value of the losses has already been considered, right? Then we have I, we have A, okay, which is the area. Okay, then we also have EP, right? Okay, which is the area of the pre-stressing tendon, right? So which, as for this example, we are going to consider this as ASL. Then we have FYK is 500 and FCTK, K, which is the tensile characteristic tensile strength, K, of our section is 2.2 Newton per millimeter square, right? So the VED value here, K, is calculated, K, based on this uniformly distributed load, K, which is 40 kilonewton per meter. So how we are going to calculate the VED value is actually a simple calculation, okay, which is using the WL square over 2 equation, right? So we have here 600 kilonewton, okay, as our subjected shear force, right? Okay, and the section that is given here, it looks almost like a T section, right? Okay, whereas we have the height of 1,500, okay, and also we have the width of the largest flange width of 1,000, right? And this is the location of tendon at the supports, okay, whereas we have this eccentricity E, okay, of 300 millimeters. Okay, so here, okay, we can see, okay, that we are going to start, okay, with the calculation, okay, whereas okay, so we have here, okay, is the VED value, right? Okay, then check the shear reinforcement, whether the shear reinforcement is required, right? So we are going to go for the flow chart just now, right? So we are going to compare, okay, the value of VED, okay, with VRDC first, okay, right? So whereas we have this VED, we are going to compare with VRDC using this equation, right? So D, okay, is calculated at this value, okay, whereas we are considering this D or the effective depth, okay, at the support, and the calculation is shown here, right? Okay, so we have here D is considering the location of the tendon at the support, right? So we have D which is 1,500, which is the total height, minus with 850, okay, this location, then plus with 300. So we have 950 as the D value, right? So since we are designing for the shear reinforcement, okay, whereas the maximum shear usually happens near the support, right? So therefore the D value should also be calculated to the location of the tendon at the support, right? Okay, so then we can substitute, okay, the value into the K equation, right? So we have 1.46, right? Then we have rho L, all right? So calculate rho L, and as for this, okay, we are going to get the rho L value of 0.0242. Okay, so this value of rho L is limited to 0.02. Right, so therefore this value is larger than the limited value. So therefore rho L is taken as 0.02. Okay, which is the maximum value. Right. Then we are going to calculate also the sigma CP, right? So in the question, we have already been given the pre-stress force value of the losses, okay, which is 2,590. Okay, then multiply this with the partial factor of safety for the pre-stress force, right, which is 0.9. So 0.9 times with 2,590, okay, then divide by the area, right? So this is the area of our concrete section, right? So we have here 4.66, right? So compare 4.66 with the value of 0.133 times with 35, right? Okay, so we need to calculate this as well, right? So therefore we are going to use 4.66 in the equation, right? So based on that, okay, we are going to substitute all those values in the equation and we will get 202. Right, okay, so as for this example, okay, it is not shown here, okay, on the next equation of VRDC minimum, okay, which is VRDC equals to 0.035 and so on, right? Okay, but this value, okay, that we have already calculated here exceeds that VRDC minimum value, right? So VRDC minimum, right? So therefore we are going to use this, right? Okay. So next, okay, we are going to check, okay, with this VRDC value, okay, which is due to the special case value, okay, since we have a single span beam, right? So therefore, we are going to calculate this as well, right? So this is the first one, okay, then this is the second equation, right? Okay, so we are going to calculate this as well, right? And we are going to compare, okay, between these two values, which one will give us the lowest value, right? Okay, so substitute the value of sigma CP, right? Then we have FCTD, right? So as for this FCTD, okay, since this is the design tensile strength of the concrete, so we are going to use this equation, which is FCK divided by gamma C, right? So this gamma C is the partial factor of safety for concrete, right? So we have FCTK, right? Because that is FCTD. So this is FCTK. So it's 2.2 divided by 1.5, right? So this is the partial factor of safety of concrete is 1.5, right? So here we have 1.47. Okay, then we are going to consider alpha 1 K equals to 1. Okay, whereas we are considering a post-tension tendon, right? Okay, so that is for the shear resistance. Okay, so here, okay, we are going to calculate, okay, these values, okay, and we are going to compare, okay, which one will give us the lowest value, right? Okay, then this is the next one, okay, whereas we have the shear strength including the shear resistance of the inclined tendon, right? So the vertical component of the pre-stress force, okay, P sine beta, okay, where B is the tendon slope. Okay, so the tendon profile, okay, is y equals to c times with x to the power of x square, right, with the origin of the cable profile taken at midspan. Okay, hence at x equals to 15,000. Okay, so this is half of the span length. Okay, as for this example, okay, the total span length is 30 meters, right? So half of it is 15,000. Okay, then we can also calculate for the y value. Okay, whereas we have the location of the tendon at midspan, right? So this is the eccentricity of tendon at midspan, and this 300 is the eccentricity of the tendon at the ends, right? So therefore, we have this y value of 450. Right, so this y equals to c times with x square, okay, is actually the equation that is particularly for a parabolic curve, right? Okay, so we are going to use that, okay, in order to calculate the vertical component, right? So as for this, okay, example, okay, we are having this eccentricity, right? So at midspan we have 750, and also at the end span, okay, we have this, okay, so therefore we are going to consider this region, right? So that's why we are calculating this y value, okay, whereas we need to know this height, okay, of our parabolic curve, right? So 750 minus with 300, 100, right? Okay, so here, okay, we are going to calculate, right? Here, we are going to calculate for this constancy, right? So we already know the values of x and also y, so therefore we can determine the constancy of 2 times with 10 to the power of -6, right? So therefore, okay, the tendon profile is equals to this complete equation, okay, together with the constant, right? Okay, then we can calculate the tendon slope, okay, whereas we are going to differentiate the equation, right? So we have dy dx equals to 2cx, right? So at the end, okay, we are going to have, when we substitute the value of c, okay, into the dy dx equation, right? So therefore, we are going to get the slope, okay, of equals to 0.06. Okay, and this slope 0.06, okay, is equals to tangent beta. Okay, whereas we are considering, okay, this slope here, right? So we have this slope, and this slope is considered as the beta angle, right? And okay, hence we have beta is equals to 3.43 degrees, right? So calculated based on this, okay, and this tangent beta is actually almost similar to the sine beta, right? Okay, so we are going to use the same value, and therefore, okay, we are going to have the vertical component Vt, or pre-stress force at the support, can be determined based on this equation, right? Okay, so we have the value of this P, right? So this is the pre-stress force, right? Okay, which have already considered the pre-stress loss, right? So we have the pre-stress force, okay, of 2590, okay, which is considered as the resultant force, right? Okay, that is acting, okay, at this location, right? So it is almost like this, okay, which is considering the trigonometric concept. Okay, so we have the resultant, okay, of 2590, right? So what we wanted to determine, okay, is this vertical component, right? Okay, so therefore with the beta value, okay, of 3.43, right? So therefore we can calculate the value of Vt, right? So since sine beta is almost equals to tangent beta, right? Okay, so therefore we can rearrange the equation, okay, to be like this, right? Okay, whereas we have replacing this value of 2590, right? So therefore we get this value Vt is equals to 155 kilo Newton. Okay, whereas we have sine beta, k is equals to Vt over 2590, right? Okay, so rearranging that equation, so we are going to get this. Okay, right? So that is for the Vt value. So what is the purpose of having this Vt? Okay, it is actually to determine, to be added up, okay, to this VRDC value, right? Okay, so just now we have already decided that we have the VRDC, the lowest value of VRDC is 202, right? Then plus with Vt, right? So this Vt value is 155, right? So therefore, we have so this 155, okay, please do remember, okay, that we also need to multiply this with the partial factor of safety for the pre-stressing force, right, which is 0.9. So 0.9 times with 155, right? So therefore we have a total of 342 kilonewton at the supports, right? So this value, okay, of VRDC, okay, is to be compared, okay, with the VED value, okay, that is from the from our section. Okay, so this is the provided or subjected value of shear force, okay, of 600. So VRDC, okay, that we have here is lesser, okay, than the VED value, right? So therefore shear reinforcement is required, right? So if we go back, okay, to the a flow chart, right? So we have here, okay, so we know that VED, okay, is now larger than VRDC, therefore we are going to follow this flow, okay, whereas the next step is for us to calculate the VRD max value. using the theta value of 22 degrees, right? Okay, so we proceed from there, right? So that is for the VRDC. Okay, right? So next is the calculation of the VRD max. Right. So a check must be made to ensure that the shear force does not cause excessive compression to develop in the diagonal struts of the assumed truss. Right. So therefore, we are going to use this equation of VRD max 22 degrees. Right. So this is the equation, okay, where we have already substituted this angle. Right. Okay. So after that, we are going to substitute key the values of alpha CW, right? So this alpha CW depends on the magnitude of sigma CP, okay, that is given by this equation, right? So we have to calculate sigma CP first, okay, then we are going to determine, okay, the value of alpha CW based on the range, right? So if we go back to the previous slide, right? Okay, so we can see that when we talk about the equations for VRD max, right? So this alpha CW, okay, is depending on this range, right? So we can see here that we have this range. Okay, so therefore what we have to do first is that we have to calculate the sigma CP first. Okay, and we are going to compare with this range in order to determine which equation, where is my pointer? Okay, right? So which equation, okay, to use in order to calculate the alpha CW value, right? So that is what we are talking about just now in the example, right? Okay, so we go back to the example. Right, so here you can see that we have sigma CP is equals to 4.66 Newton per millimeter square. So then we are going to compare, okay, with the range, okay, and we have the range giving us this equation for the alpha CW equation, right? So we are going to use this. Then we are going to just substitute, okay, the value of sigma CP and also FCK, and we get alpha CW is 1.2. Right, so this value is to be substituted into the equation of VRD max 22 degrees. Right, so we have 1.2 here. Okay, then other values should be substituted as well. Right, then we have all this, okay, and we have here 638 kilo Newton. Right, and again this value is to be compared with VED. Right, so we know that here VRD max is larger than VED. Right, so therefore, okay, we can proceed to the design of the shear reinforcement. Right, so if we go back to the flow chart, right, so we can see here, okay, that we have VED is lesser than VRD max, so therefore we are going to follow this flow. Right, so straightforward we can use this equation, okay, which is ASW over S. Okay, right, so as for this, right, so here is to calculate the area and spacing of links, okay, whereas where the shear force exceeds the capacity of the concrete section, allowing for the enhancement for the inclined tendon force. So shear reinforcement must be provided to resist the net shear force, taking into account the beneficial effect of the inclined tendons. Right, okay, so just now we have already considered the VT value. Right, okay, so here we are going to calculate using the using this equation, right? Okay, because we know that shear reinforcement is required, so therefore we are going to calculate this, right? Okay, so ASW over S, K is equals to VED over 0.78 D FYK cotangent theta, right? So since just now the VRD max is considering 22 degrees, right? So similarly for this calculation also, okay, we are going to use this angle. Right, so we have here 600 minus with 0.9 k times with 155, right? So that is for the VED value, right? So we are going to consider, okay, the value of the vertical component, okay, just now, right? So this is our shear force, subjected shear force. So deduct, okay, with the vertical component, okay, that is due to the inclined tendon, right? Then we have 1.95D, okay, times with FYK, right? So this is for the bottom portion, right? So calculate that, okay, then we will get the ASW over S equals to 0.497, right? Then we are going to calculate also, okay, the minimum length, okay, requirement, okay, whereas we are going to use this equation. Okay, so this minimum length requirement, okay, we are going to use this minimum length even though the shear reinforcement is required. Okay, this minimum length is to be provided at the sections, okay, whereas we have lesser value of the shear force, right? So we know that in a simply supported beam, right? So we have UDL, okay, on top of our beam. Okay, then we have the shear force. Okay, the shear force diagram that looks like this, right? So therefore we have positive and negative values. Okay, so the maximum value, okay, happens here, okay, which is near to the support. However, at midspan, okay, we have very minimal value of shear force, right? So at this point, here or at this region, okay, we can just provide, okay, this minimum reinforcement, okay, or minimum lengths, okay. So we do not need to provide very high values of or very closely arranged links, okay, but we can just put some loose links, okay, that is to cater only for this minimum links, okay, that is going towards 0, right? Okay, so we can save some cost here, okay, in the provision of the links, right? So you can see here that we are going to calculate this as well, okay, and we will get ASW over S equals to 0.14. Right, okay, so please bear in mind, right, so this ASW value, okay, in a section, okay, in a beam section, okay, can be calculated using this equation, whereas we have 2 times with pi d squared over 4, okay, whereas this d is the diameter of the length, okay, and this 2 is considering, okay, the 2 legs of the length, right? Okay, so we are considering the cross sectional area of the length here, right? So this is how, okay, we are going to calculate the value of ASW, right? Okay, so these are the range, okay, of the ASW of ASW over S, right? So therefore, provide 10 millimeters lengths at 300 millimeters centers, right? With ASW over S equals to 0.523, right? So this is the value, the new value that is already been calculated, okay, based on this. So you can see here that the provided area, okay, must be the provided range, okay, must be larger than the required range, right? So the required range is 0.497. So therefore, the provided range is ASW over S equals to 0.523, right? Such that the shear resistance of the links actually specified, K as V minimum, K equals to ASW over S, K times with 0.78 dFy K cotangent theta, right? So this V minimum value, K, is actually calculated, right, based on this equation, right? So we are rearranging the equation, okay, this equation actually, right, rearranging the equation in order to get this value, okay, of the V minimum. Right, so this V minimum is actually considering, okay, the minimum length that is provided in our section, right? Okay, then calculate the additional longitudinal force, right? So this is the last one, right? So if we refer to the flow chart, right, this is the last one, okay, which is at the most bottom. Right, so we are going to calculate the longitudinal tensile force, right? So by substituting all the values of VED and also the cotangent theta, right? So we will have 575, right? And from there we can calculate the value of ASL, okay? And we get here 1322, right? Okay, so this additional longitudinal steel can be provided, okay, by 4 untensioned hitch 25 bars, okay, with the area of 1960, located at the bottom of the beam's cross section, fully anchored past the point required using hooks and bends as necessary. Right, so untensioned longitudinal reinforcement must be provided at every section, okay, to resist the longitudinal tensile force due to shear. Okay, and the above calculation must be repeated at sections to determine the longitudinal steel requirement. Okay, right, so you can see here, okay, that this is the table, okay, of the shear calculations at 3 meters interval. Right, so usually if we have very long span, right, so as for this example, we have a span of 30 meters, right, so therefore we are going to have several points, okay, or several locations that we are going to calculate for the value of shear. Right, so you can see here, as for this calculation that is shown here, okay, we are going to have the location at midspan, okay, then we have 3 meters from midspan, 6, 9, 12 and also 15. Right, okay, so we are going to calculate the values, okay, depending on this D value. Right, so this D value will actually depend on the location of our tendon. Right, so since it is an inclined tendon, right, so when it is of a parabolic profile, so therefore the location of the tendons will also differ. Right, okay, then we can calculate the VRDC value from there. Right, so different locations will have different um, VRDC value. Okay, then we can calculate the pre-stress values, okay, and also the VRD max, okay, and we can determine the ASW and also AS minimum. Right, okay, so you can see here that different locations, okay, will have different reinforcements, okay, shear reinforcements to be provided. Right, so not to worry, okay, if this is actually when we talk about the practical calculation, okay, that is done in the exact design. Okay, however, in your tests, right, so or in your exams, okay, you will be only required to calculate, okay, or design for the shear reinforcement at certain points. Right, so meaning to say that you do not need to repeatedly calculate using the same equations, okay, but you can just simply use the a certain values. Okay, wait. Okay, sorry. Right, so okay, so as for the arrangement, okay, of the shear reinforcements just now, right, so considering all the locations, okay, that we have already calculated, so we can see that the shear reinforcement, okay, that has been designed, okay, is actually placed at the near the support right here, which is H10 300. So this is near the support, okay, whereas the shear force is maximum. Okay, then towards the midspan, right? So the um, shear reinforcement, okay, or the shear or the yes, the shear reinforcement is reduced, okay, to H10 450. So you can see here that the spacing, okay, is more further apart, right? Okay, sorry. Right, so then we also have this, okay, as considering the minimum lengths, okay, whereas we can see that the diameter, okay, of the length has been reduced to H8. Right, so instead of using H10, so we can reduce to H8. Okay, and the spacing is also 450. Right, so you can see that we have a difference there. Right, okay, in order to apply the cost saving. Right, okay, so we only apply the this H10 300, okay, the shear reinforcements only at the critical locations. Okay, so for a more non-critical locations, okay, such as the near the midspan, okay, we can reduce the area of the reinforcement. Okay, right, so as for self-assessment, so what I want you to do, okay, is that I want you to check the shear resistance, okay, of the pre-stressed concrete beam in the example 4 Magna diagram, okay, that we have used previously. Okay, and in the example we have already determine the pre-stress force, and using that value, I need you to check the shear resistance, whether we are going to require the shear reinforcement, or we are going to require the only minimum reinforcements, then try to propose the required shear reinforcement for the section, right? So basically we are going to go through the same process. We are going to just you are going to just follow the flow chart, right? So this is just what I want you to do, just to check your understanding, on this topic that we have discussed today. All right, so basically what I want you to try today, is to check the shear resistance first. So no need to propose the reinforcement yet. But just check the resistance, meaning to say that we are going to compare, between the value, sorry, so the value of VED and compare with VRDC first, and see whether the shear reinforcement is required or not, right? So we are going to stop here, right? So this will be the last part, in the design of a pre-stressed concrete beam, whereas we have already learned, on how to check the shear resistance, for the beam, under the ultimate limit state, right? Okay, so with that, thank you very much. Assalamualaikum.